Dear attendees of the DigiCrop Conference 2022, my name is Vereecken, and I will give you a presentation on managing agricultural fields from observation to prediction. I first want to thank the organizing committee for having invited me to giving this talk, and of course my colleagues who joined me in this effort to presenting and making this work happen. Just the motivation for why we are doing this work. So we have current technologies available that provide unique opportunities to manage agricultural systems, and these include new satellite platforms, hydrogeophysical techniques, and ground-based remote sensing. In addition, we have data simulation techniques that allow us to forecast the evolution of terrestrial systems and to inject near real-time observation observed by these technologies into models. Still, the use of these models is hampered by parameterization of soils and their spatial variability, as it's still a big challenge, and it is extremely important to predict crop growth by knowing this information. And finally, closing the yield gaps and reducing agricultural environmental footprint is at stake, because if we want to close the yield gap, typically we have to intensify our management, and this might have negative impacts on the environment. Just a brief explanation of what the yield gap is for crops. So we have a potential yield, which is mainly determined by the atmospheric conditions and the type of cultivar. And then we have limitations. We have eventually water as a limiting factor that then yields a water limited yield. And then we have water and nutrients that might be limiting, which then leads to an even lower production, which is then water and nutrient limited. And then we have the actual yield, which is also controlled by the management. And our aim is of now that we want to close this gap between actual yield and the potential yield. And for this, we need to improve on our water and nutrient management as one of the key aspects. But also the knowledge of the biophysical environment, for instance, of soil properties and their variability in space and time, is extremely important. And in the next slides, I will show you how one can characterize the spatial variability of these soil properties and how we can bring them into the models to predict yield. And then also I will show you examples of how we can use sun-induced fluorescence to improve the water stress prediction of crops. So two examples: characterizing the impact of soil variability and estimating root water uptake parameters from sensing information. Now, there are currently many techniques available that allows us to map soil heterogeneity. There are, for instance, the electrical resistivity tomography, which uses electrical currents to measure the bulk electrical resistivity of soil and then relate this to soil properties. We have ground penetrating radar that typically measures the soil moisture content. And we have electromagnetic induction, which also aims at characterizing the bulk electrical resistivity or conductivity of the soil, and from there then derive soil properties. Now, why use EMI? EMI has the opportunity, the possibility to be highly mobile. It can be towed by vehicles, and it has already proven experience in characterizing agricultural fields. As said, EMI typically measures the bulk electrical conductivity of the soil, and it then needs to be correlated to, for instance, the soil texture and the water content in the soil profile. And typically this measurement system is mounted on a sledge. It's connected to a GPS system and it's dragged by a quad motorbike, and it then allows you to characterize the spatial variability of the plot that has been surveyed. And on the right hand side you see a graph, and this graph shows the spatial distribution of electrical conductivity of a selected field site near to the research center Jülich, which we will use in the subsequent to demonstrate the potential of how this information can be used to inform crop growth models. Here's an example, a more detailed view on the soil heterogeneity of the environment. It was a picture taken by Rapid Eye in 2011, which dry spring, where you can see subsurface patterns of soil emerging and leading to differences in leaf area index. And we've used this field site to use our EMI technology to characterize the spatial variability. And for that site, we also have common soil maps available that we will then use in a comparison to see how well or how good the information of the mapped spatial variability of soil properties is using EMI. So what we do is we map with EMI the spatial variability of the bulk electrical conductivity. We then do an image classification in order to obtain management units, which were then characterized by sampling, so that we have for each management unit a typical soil profile. We then use the Agro-C model, which is a combination of a water and solute transport model combined with a crop growth model and a carbon model to model the water content. And from that, we also are able to predict the productivity. In this case, for the year 2016, you can see the simulation emerging as time goes on. And just by visual inspection between the left lower panel and the simulation, you can see that we are basically retrieving some of the spatial structures that we see in the productivity or in the leaf area index. It's important to note that we account for the effect of stress by using a stress factor, which is optimal between certain metric potentials. If it's too wet, then we have reduction due to stress of too much water. And if it's too dry, water uptake is then also reduced. We will later use this also in our work on the solar fluorescence. Now, how good are these simulations? And this is shown by comparing the simulated leaf area index with the observed leaf area index from satellite data. And the upper panel shows the simulated results for different dates during the growing season of different crops. And the lower panel show the observed one. And just by visual comparison, you can see that the simulated leaf area index values pretty much match the observed ones. And this is a good finding because it's not only done for one crop. You see the crops above, it's sugar beet, potato, winter crops, corn, winter barley, and winter wheat. We then use this model to simulate the productivity at harvest. And this is done for 4 crops: sugar beet, silage maize, winter wheat, and winter barley. And we have done this for specific field sites where we also have information from the farmer on the productivity. And the percentages show that if you have 100%, the maximum productivity was reached as there was no water limitation. And that you see then, of course, that we have areas where we have reduction in productivity due to water limitation, which is mainly caused by the type of soil profile in terms of the vicinity of groundwater level or groundwater and or the absence of groundwater. And we found that for sugar beet and winter wheat, the data actually pretty much resemble the harvest data. For corn and winter wheat, we have some more deviations, but they still correspond to literature values. Now we wanted to explore the potential of using these geophysics-based soil maps compared to the soil taxation map, which is still used in Germany to assess the productivity of soils, and a typical soil map of 1 to 5,000. And we run different simulations with the model we used before to see in how far this information improves the observed values of productivity. And here we have used as a marker for productivity the leaf area index. And you can see that we have strong improvements for crops, summer crops, and over different soil heterogeneities. So that means, for instance, the summer crops simulations improved when we use geophysics-based information compared to the 1 to 5,000 soil map or the soil taxation map. And also in case that we have heterogeneous soils, we see an improvement when we're using geophysics-based soil maps compared to the 1 to 5,000 or the taxation map. This is just, you can see this by just comparing either the R-square or the root mean square error, which should typically decrease as we are improving in our prediction of the leaf area index. For winter crops, the improvement is less clear. So this provides farmer with interesting information on how to manage his soils, especially those that are heterogeneous. Now let's look at an example on how we can use irrigation, as we've noticed that water stress plays a role in reducing productivity. It would be good that we would be able to enhance its productivity by irrigating the fields. And for this, we need to have information on when to irrigate. And we define here a stress level for irrigation that is equal to 80% of the potential evapotranspiration of the crop. So if the stress factor drops below 0.8, then irrigation should be turned on. We do this here, we show this for simulations, and we assume that we have a perfect 7-day forecast. And here you see the crop growing in July and August, and at a certain moment in time, the crop reaches a stress factor which is lower than 0.8, and one then should apply irrigation. This is shown by the green arrow, and you see again, once you irrigate, then the stress reduces, the crop keeps on growing. Again, you get a stress, you apply irrigation water, and you reduce the stress factor, and you continue doing it until harvest. Now, if you use this information, you can show that you have an increase in productivity on many field sites, which is about 30% more in terms of wet biomass production. So that means that using these technologies, one is also able to improve the productivity, but also to manage his fields in an economical and environmental way. Second example I wanted to show was the use of unmanned automated systems, which in this case are drones, which we then use to obtain information to inform our models. Typically, these drones are equipped with either an RGB camera or a thermal camera. It can also be a multispectral camera that provides information about the crop canopy. But in this case, we will talk about sun-induced fluorescence as a way of measuring the gross primary production of the crop, to quantify the photosynthesis, and to look at the effect of water stress on photosynthesis. So fluorescence is the outcome of the radiation of sunlight onto the canopy, and sunlight is used to drive the photosynthesis apparatus, which then leads to biomass production. And there are, of course, some spin-off of this sunlight emission, which is the fluorescence, which is not used for photochemical reactions. And there has been a breakthrough in spectrometry which allows us to measure the sun-induced fluorescence in the oxygen A and B bands. And this allows us to detect stress at an early stage, drought stress in this case. So here is a scheme on how we use the SIF on canopy scale. So we have solar irradiation. This produces photosynthetic active radiation, and a part of that is absorbed by the chlorophyll that is then used for photosynthesis. And the stress, of course, changes the leaf biogeochemistry. So when sunlight hits the canopy or the leaf, we have photochemistry, which produces which drives the photosynthesis mechanism. We have then also heat that is dissipated, and we have chlorophyll fluorescence that is produced. Now, if stress is happening, and that can be any kind of stress, then this leads to a change in the magnitudes of the heat and the chlorophyll fluorescence. And what we measure with our drones are two fluorescence signals. One is called the SIF-A and one is called the SIF-B. In this case, we will use the SIF-A signal at a wavelength of 760 nanometers. And this information is obtained from drones and injected into a simulation model to estimate the parameters that define the stress function. And this is shown schematically here. We again use the Agro-C model. We have this water stress function that tells us how water uptake depends on the pressure head, and we have an optimal zone which is equal to 1 with lines between the pressure head potentials 2 and 3, and we are typically interested in estimating this metric potential 3, which is typically unknown but which can be derived from fluorescence signals. And then we have a mathematical model with Agro-C and also a scope-based model that allows us first to simulate the fluorescence and match this with the observed fluorescence from measurement system. And what we do is we minimize the difference between what we model and what we simulate by adjusting this H3 parameter. And this allows us to get better predictions of, for instance, netto ecosystem exchange. This is the way the system works. We have the SIF observations. This can also be mounted on a drone. We optimize the difference between what we simulate and what we observe. We get an optimal stress factor, and then this allows us then to generate water and carbon fluxes at the field site. This is shown here as an example, as an outcome. You see here over different days of the growing season, the observed sun-induced fluorescence, which is the black dot. Then we have the simulations in which we assume that we have no stress. And then we estimate from the observations the parameter H3, which then allows us to account for stress effects. And you see that we are improving on our prediction. And the same is here for the netto ecosystem exchange. This is related to CO2. That basically means this is the net flux that we observe from a field site. And typically it means if you have a sink, then CO2 is being uptaken. If it's a source, you release CO2. And we see here that the observations show that we have a CO2 sink, and that if we account for no stress, this is much larger, this uptake. And if we account for the SIF-based H3 estimate, then we are improving our predictive capability of the netto ecosystem exchange. And this shows us that we have information in the sun-induced fluorescence to improve our models and to better estimate, for instance, also productivity. Come now to the outlook. I think that we have shown here that when we consider high resolution soil heterogeneity, this may lead to an increased crop yield and may provide interesting information on how to manage irrigation systems. Combining new observation technologies with advanced crop growth models offer the opportunities to reduce the yield gap. And we have shown that this can be done by using data simulation and crop growth information, and that this offers a potential to forecast crop yields. With this, I would like to thank you for your attention, and I'm happy to take any of your questions.